Hello, this is Eli Hertz, and today I'm going to be solving for the equations of motion of a pendulum using Lagrangian mechanics. So I actually took a practice problem for this, and I'll link it in the description. It's from MIT OpenCourseware, and it's from the class for Classical Mechanics 2. And basically, there's three parts of the question. I'm going to be doing the first part in this video, and I'm going to be doing the second two parts, or I guess the second and third part in the next video. And the first part is going to be using the Euler-Lagrange equation to derive the equations of motion for the pendulum. Now, the Euler-Lagrange equation is partial L over partial Q, where Q is some generalized coordinate, and I'll talk about what I'm using for that soon, minus the time derivative of partial L by partial Q dot, where Q dot is the time derivative of that coordinate Q, is equal to 0. And that's the Euler-Lagrange equation. If anyone in the comments would like, if you guys want to, I can do a separate video deriving the Euler-Lagrange equation, but for now, we're just going to take this as kind of our equation that we're using. I'm grabbing my eraser here. And so, what is the Lagrangian, first of all? The Lagrangian is a object in physics, and it is the kinetic energy of a system minus the system's potential energy. And I mentioned that I'm going to be solving this for the pendulum, so what exactly are those? So, first, when doing a physics problem like this, I always like to draw it out. You have a mass m hanging on a string, and we'll take this line right here, this vertical. We're going to say that it's at some angle theta from the vertical. Now the forces acting on this are obviously tension from the string pointing towards the pivot right here, and there's the force of gravity mg acting downwards. Now normally in classical mechanics we'll set up F equals ma, we'll do all the net forces, and we'll solve for an equation of motion. However, for Euler-Lagrange equation, we plug the kinetic and potential energies in the equation for the Lagrangian, and then we take the derivatives to find the equation of motion. So what I'm actually going to do is I'm going to say, okay, the Lagrangian here is the kinetic energy, which is 1/2 mv squared minus potential energy, which is mgh. Now, I'm going to change this up a little bit. From rotational mechanics, I'm going to use V is equal to L omega. Now, omega is the angular frequency, basically the speed at which the angle changes, or the rate at which the angle changes with respect to time as something moves in a circular pattern. Specifically, as this pendulum here, as its angle is changing, it changes with some speed, and that's what W is. It's the time derivative of that angle theta. Anyways, I'm going to make that substitution. V equals L omega. What is L? L is the length of the string in this case. And so this term is going to become 1/2 m L squared omega squared. Because if you have L omega parentheses squared, since they are multiplied together, you can distribute the square, and you get L squared omega squared. And then the next part, I'm going to simplify this H term right here. If we have, and I'm going to be drawing this out quite a bit, this pendulum right here, and this angle theta, you can kind of trace out the rest of its trajectory. It's going to be a circle. It's going to be the arc of a circle. And when it's at this point here, this height from the ground here is going to be equal to the length of the string, which I'll label right here. That length is L. But right now, where it's at right here, this height is greater than 0. And so we could say that these two right here, this length and this height h is the same as L. Now what is this height h here? You can just use basic trigonometry, so Katoa, to figure that out. This is the hypotenuse L. With respect to the angle theta, this right here is the adjacent, and so you would say this is equal to L cosine of theta. Now I said that these two add up to L, and so you can then make the substitution that L is equal to H plus L cosine theta. And then we can do some rearranging, subtracting L cosine theta from both sides, and we get that H is equal to L minus L cosine of theta. And so we get to plug that in for H here. MGH becomes MGL, and I'm going to factor out L from this. It's going to be 1 minus cosine theta. So MGL times 1 minus cosine of theta. So that's there, if you can see that. And then it's subtracted from this quantity right here. So now we have a new Lagrangian, which is written in terms of omega and theta. Now, this kind of gets back to the generalized coordinates. Earlier, I used Q and Q dot as my general coordinates. I'm going to be substituting in theta for Q, and obviously the time derivative of theta, omega, for Q dot. And so now I'm going to erase this. Take one last look at this before I erase it. I just dropped my eraser, great. Anyways, I'm going to rewrite the Lagrangian and the Euler-Lagrange equation in terms of those coordinates now. So, dl I originally had by dq, but I'm replacing that with d theta minus d by dt dl by d omega equals 0. And that's our new Euler-Lagrange equation that we're going to be working with. All I did was substitute in theta and omega for the coordinates. And then our Lagrangian, as it was just written, is 1/2 m L squared omega squared minus, I'm just putting it here so I have more room, mgl times 1 minus cosine of theta. And so how do I find the equations of motions using this equation right here? I plug in L to these derivatives, I compute them, and then whatever's left of this equation after I do that is the equation of motion. So the first thing I'm going to do is compute dl by d theta. Now, I will mention, since this is a bit longer of a derivation, I have handwritten notes right here that I will be linking in the description as well. I'll put a PDF or something there, and if that doesn't work, I can make a community post with just a picture of it. But if somebody needs a reference or something to go back to, I will have that posted, and I will put a comment under the video telling where I put that. But that's for after. So how do I compute dl v theta? Well, you just take the partial derivative with respect to theta of that Lagrangian. Now, if you're confused on what a partial derivative is and how it differs from regular derivative, I have a video for that, so if you want to check out my video for that on my channel, that is there, and that explains what this is. Anyways, we're going to plug in the Lagrangian. This is 1/2 ml squared omega squared minus mgl times 1 minus cosine theta. Now, since it's partial derivative, everything that isn't theta is treated as a constant. And so this whole term here goes to 0 because it doesn't include theta at all. However, this term right here, we take the derivative of that with respect to theta, the derivative of 1 minus cosine theta is negative, the derivative of cosine theta is negative sine theta. These cancel out, and so you get a positive sine theta. And so what that becomes is negative MGL sine of theta. And that is, sorry if I'm covering it here, dl d theta. Just so I don't forget it, I'll write it at the top right here. Theta equals negative MGL sine theta. That I can save for later. The next step is computing dl by d omega. To do that, same thing we just did. Plug in the Lagrangian for L. 1/2 mL squared omega squared minus MGL times 1 minus cosine of theta. In this case, there's no omega term here, and so this term goes to 0. However, this term does not. The derivative of omega squared is 2 omega. And so what we can do is, since this is a constant, we can pull it out, and we can say that this is equal to 1/2 mL squared d by d omega of omega squared. Using the power rule, this becomes 2 omega, and the 1/2 and the 2 cancel out. And so we're left with mL squared omega, which I'll write over here. So dl by d omega equals mL squared omega. Again, if any of this is hard to follow, I will be posting handwritten notes. Now, if you remember correctly, the Euler-Lagrange equation called for the time derivative of this term, and so that's what we're going to do. So we have d by dt of dl by d omega, and that is the same thing as d by dt of mL squared omega. Now, if you remember correctly, mL squared is a constant. We can pull that out, and so you get mL squared d by dt of omega. Now, for anyone who has taken a classical mechanics course or anything involving rotational mechanics, it would follow that d by dt of omega is a quantity we call alpha. Alpha is the angular acceleration of something orbiting in a circle, or really anything orbiting, or anything rotating. Sorry, orbiting is a more specific case. But basically, it's the rate at which the angular speed changes with respect to time, aka the derivative of the angular frequency with respect to time, or angular velocity, not angular frequency. And it's the second derivative of the angle with respect to time. And so I'll rewrite this up here. We have d by dt of dl by d omega equals mL squared alpha. And so now we can plug this back into the Euler-Lagrange equation, which, if you recall, is dl by d theta minus d dt of dl d omega is equal to 0. And now we have our values, specifically this and this, we're going to plug in. And so, if we plug these in, we get negative MGL sine theta minus mL squared alpha is equal to 0. And adding mL squared alpha to both sides, we can rearrange this and get negative MGL sine theta is equal to mL squared alpha. And that right there, that differential equation right there, is the equation of motion for our pendulum. Now I'm going to make one last substitution. If you recall, I was just talking about this. Alpha is the second derivative of theta. And so I'm going to replace alpha with theta double dot. What do these two dots mean on top of theta? Well, it just means that it's the second derivative of theta with respect to time. It's just a notation. I could have just as easily wrote omega, for example, as theta dot. So this right here is a second order differential equation, and it describes the motion for a pendulum with constant length. And that's it. That's the first part of the question. In the next video, I will be discussing a simplification you can make to solve the differential equation, and then I'll actually be solving it and solving for theta as a function of time. But that's it for now, and if you have any questions or concerns, leave them in the comments. I'll be posting handwritten notes, and that's about it. Thank you very much for watching, and this is Euler-Lagrange signing out.